So my presentation is named ClickHouse for AI, but let me clarify. I am not an AI expert. I am just a ClickHouse developer. But when I do AI, I am doing it in ClickHouse. So what can we do inside ClickHouse related to AI? We can actually run AI models inside the database. But we are not going to train our models. Let's use pre-trained models just for the inference. Then we can apply ClickHouse for semantic search. Actually, semantic search is just a single use case related to AI, how ClickHouse can be applied in this area. Many companies are using ClickHouse for data preparation, data profiling, data cleaning before the data is used for model training. Many companies are using ClickHouse for ML ops and ML observability, such as weight and biases, length chain, etc. And semantic search is just a single use case around AI. So, and to do this, we have a feature in ClickHouse. It is not a new feature, it exists for several years. User-defined functions. And we have a couple of types of user-defined functions, such as regular functions that you can use to process data, as other functions like plus, minus, and you can introduce your own function, like my function. We have user-defined table functions. They can process a query result with an arbitrary script that you write. And then you process the output of this script further. We have user-defined dictionary functions, also with custom scripts. You can create a dictionary with executable engine. And then you can use it as your dictionary data source. We also have SQL user-defined functions. You can write create function, the name, as, and a lambda expression. In this example, this function takes a single argument, a string, and returns, what does it return? The number of white spaces. And then we can use this function like this, and it should return 1. SQL user-defined functions work for simple expressions. They don't support recursion, they don't support loops, complex logic, but they are easy to use. They are totally not suitable for AI and ML. So let's skip it. And another category is executable user-defined functions. In this case, you can use any programming language, Python, Node.js with JavaScript, TypeScript, Go, even Rust, if you want to try something interesting. But for AI, probably the first choice will be Python. In this example, it is also not anyhow related to AI. We just reproduce the same SQL function to count the number of white spaces. The script will accept arguments to standard input, serialize it as a table in the desired format like TSV, JSON, protobuf, or Parquet, and you return the results in the same format. In this case, it will print numeric data as is, so it is probably tab separated. You provide the configuration in the server configuration. You define the type of the function, the name, format, the command to run. You place this file inside a special directory named user scripts, and the types of arguments and return values. And it works. The script will run for each block of data. and it will be automatically parallelized. If you specify max threads like 10, then it will run 10 scripts in parallel. It will be automatically batched. So if you have block size of 65K records, these 65 records will be piped into your script. And the configuration is reloaded without server restart. Let's measure the performance. So in the first example, we use a SQL function, and the performance is 1.30 billion records per second. It's quite nice. At least there are billions. Okay. In the second example, with our Python script, the performance is 40.70 million rows per second. It is not nice, but let's figure it out. You might say, okay, Python is slow, we already know that. And it will be just justifiable. Maybe it is slow due to data serialization and deserialization, because it has to be piped into a script and parse it back. But let's take a look. Maybe we can make it faster with the existing functionality. The first method is pooling. You just change the type from executable to executable pool. In the first mode, it will launch the script for every block of data, wait it to finish, read the result, then launch it again for the next block of data. In the second example, it will launch the script and keep it running, and continue piping the data into it and reading the results out of it. It avoids initialization cost, and the number of concurrent processes will be run near the ClickHouse server. So let's take a look how it will optimize our simple function. In the left example, it is executable 40 million records per second. In the right example, it is executable pool. The only difference, we have to flash after every record, because otherwise it will be difficult to know when the data ends. And it is 10 times faster, 400 million records per second. Okay, but it was 1.3 billion records per second, so still Python is slow. Let's speed it up again. Another option is chunking. By default, the format is simple, record by record, but we can enable this option, send chunk header. And in this case, it will first tell the script the size of the chunk. And then it will pipe the corresponding number of records. So the only difference, we don't have to flash after every record, we can do it after every chunk. And it is 1.5 times faster, 663. Why not 666? But this is it, just 1.5 times faster. Okay, we can also change the serialization format. In this example, we used TSV, but we can use Parquet, Arrow, raw binary format, or native ClickHouse format. It will be faster. And finally, we can rewrite it from Python to Rust, and it will be even faster. Or in C++, maybe it will be even more fast. Okay, maybe it will work as fast as native functions. But don't worry about it, because if we use machine learning models or AI, we know they are slow. They can output just maybe hundreds or thousands tokens per second. Even if we strip down the model, maybe it will be like 10,000 tokens per second, not like billions of records per second. So let's try to do it. Let's try to implement semantic search with vector embeddings. just if someone doesn't know, but actually everyone should already know what is a vector embedding. It is a way to transform any type of data, like text, images, videos, music, into a vector of a large number of dimensions, like hundreds or even thousands dimensions. So similar objects, like similar texts, will have their vector representations, also similar, close to each other, according to some metric. And the metric could be L2 distance, so Euclidean distance, or cosine similarity, or dot product, which is not, strictly speaking, a metric, but it is also a measure of similarity. So with classic text search, you search by tokens from the text. With semantic search, you attempt to search by a meaning of the data, the actual meaning. So similar data will be found anyway. Okay, this is, I already explained, the distance in the vector space corresponds to the similarity of the objects. And embeddings look like this. Let's suppose we have a function named embedding. We put a short sentence or a paragraph into this function and get this vector. It is quite large. And in this case, guess how many dimensions do we have? Could you count from the slide? 100. 100, okay. Another? 300.
250. 600.
600. Could you please be more specific? 300. 350. Could you please be even more specific? 384. But you are still the winner. How to implement this function and how to test it? To test it, I used a dataset of my favorite website, Hacker News. There are 30 million text comments that are just 7 gigabytes compressed inside ClickHouse. So the dataset is actually quite small. And the first step that we want to do is to calculate all these embeddings for every comment and the title. Let's take a look, and we will see it inside ClickHouse. So the 28 million records, and the total size is 77 gigabytes. Here is the data. And, okay, here is the data. Let's look at the next. How we will calculate these embeddings. Here is a Python script. It will load a model using the sentence transformer library. The model is quite old. It is from 2 years ago. Today you could use more advanced models. You don't have to use local models. You can also make requests to OpenAI or Claude. And what do you think? How much it will cost to make 30 million requests to OpenAI? I don't know. I did not even try. So I recommend to use local LLMs. So we load the model, and every record will be a text. We put texts into a batch of certain size, actually the same size as ClickHouse will tell, and then just encode into embeddings using this API, and output as JSON. Here we use JSON format to this output. So it is pretty simple. Let's configure it. The input type is string, the output type is array of float 32 embeddings, and the type of function is executable pool. Actually, we use tab separated format, but output as JSON, just because this array could be still read as tab separated. And we test it like here. Here is the chunk size. Here is the first record, the only record. And we pipe it into the script. Let's take a look. Select, does it even work? We name this function embed. Hello world. It works. And it is also fast, just 8 milliseconds. For some reason. If I change it, the vector will be different. Okay, something else. If I select titles from Hacker News table, I get this. Let's try to run it for all titles. We will see embed of, we will do it together, title concatenated with text. With white space in between, no, new line in between. And interesting how fast it will be. It's pretty fast. 14 milliseconds for 10 records. But I did not expect it to be slower. It is just as we want it to be. Okay, now let's measure the performance for real. I will run it for every record. And the performance is 100,000 records per second, 40,000 records per second. No, 20,000 records per second. It is slowing down and slowing down because it has to run this model for every text. Oops, it is just above 10,000 records per second. I never have seen this speed with ClickHouse. Typically it should be billions, but here we have an excuse. We run large language model directly inside it. Okay, so what about performance? With CPU instance type, even if I use the maximum available, almost the maximum available instance type in AWS, C6A32X large, actually you can get C7I48X large today, but still the performance will be just 265 records per second. If I use a cheap GPU on my old desktop, GeForce GTX 1760, you can get this GPU probably for $50. The performance will be higher, 500 records per second. If I use a pretty basic GPU instance in AWS, I will get 2,000 records per second. But then I also asked my colleague who has a gaming GPU, and he plays a lot of computer games on weekends. I asked him, could you please use it for one day just to calculate my embeddings? And he sacrificed his games just to test it. And he got 3,500 records per second. Actually, you can get more with 800, 800, and similar. Okay, let's take a look at another example. So I will create a table, and this table will contain our vectors in an array of floating 32 data type. We will use a lower index granularity because these vectors are quite large, and we calculate all the embeddings with a single query, insert select. We select everything plus these embeddings of the text. We also strip HTML elements, and this query, after just a few hours, it finished. Okay, what did we specify? What unusual did we use? Unusual configurations to run this query. First of all, we use a lower block size because vectors are quite large. And with so for example, 384 floating point 32-bit. So we have to multiply by 4 bytes. It will be about 1.5 kilobyte per vector, and if we multiply by the default block size, 65,000, it will be about 100 megabytes per block, and it does not fit in CPU cache. So we lower down this block size to make it faster. And if we process this data on GPU, it will be automatically parallelized by the Python script using PyTorch, and it will not benefit from larger batches. You will only use more memory. Okay, we use executable pool, pooling, chunking. We use quite a small pool size with just 2 processes, because the script is already parallelized internally. And let's take a look how to use these vectors. To compare vectors, we have a set of functions. L2 distance for Euclidean distance, L2 squared distance, it is slightly simpler. Cosine distance, L1 distance, LP distance when you can specify P, and dot product, which is just a scalar product. To do semantic search, the easiest example of semantic search is here. We just order by this distance. Let's take a look. We want to find the most similar comments to ClickHouse is fast. I don't want it to surprise me. I really want semantic search to work correctly. What do you think? What we will get? Okay, this query ordered by distance. To the text, ClickHouse is fast. And let's try it. Top 10. Interesting. Haven't ever heard about ClickHouse. How does it compare to ClickHouse? Sorry if this is obvious, but what is ClickHouse? Not to mention ClickHouse. Can confirm ClickHouse is generally faster across most typical workloads. If you want cost-efficient high performance, ClickHouse is hard to beat. I like these results. Okay, another example. Where title not like ClickHouse. So what will be the comments similar to ClickHouse is fast, but which don't contain the word ClickHouse, and text also not like ClickHouse. Okay, sell house fast. Chinese click farm. Wow, ClickHouse is right up there, but with white space. Okay, I don't like these results much, but look at the performance, 77 gigabytes per second. And the result is returned instantly. Actually, it is 700 milliseconds, but it feels instantly. Okay, Redshift is based off Paraxel. Okay, surf analytics data with Redshift. Building, what the query was. ClickHouse Redshift analytics database. Generally, I have an impression that it works. What if we search something similar to Hadoop is slow? Because it is slow, you should not use it at Deutsche Bank. Okay, a lot of comments that Hadoop is slow. If you are disappointed with the speed and complexity of your Hadoop cluster, and especially if you are trying to crack a bit, you should give ClickHouse a chance. It works. Okay, let's take a look at another example. We will change the block size to a smaller value. We will set max threads. The question is how to monitor the performance, the utilization of my GPU. If we calculate a lot of embeddings, the speed is, it can be monitored with a command line application named NVTop. If you are using NVIDIA GPU, and most likely you are. In this example, you can see that it is utilized. The memory is memory usage is less than 100%. So basically it works as fast as it could work with this particular script. Okay, and it is just 2.5 thousand records per second. It's quite okay. Okay, let's try some optimizations because it was fast, but I wanted to make it even faster. One optimization is quantize our vectors. We used the data type array of floating point 32 in my table, but I can convert it to bfloat16. What is bfloat16? If you look at the binary representation of 32-bit floating point format, you will see first is the sign, so negative or less than 0 or greater than 0, then exponent, 8 bits, and then the mantissa. If we just take first 16 bits, we will get a coordinate representation of the same data, and this representation is named bfloat16. It contains the same number of exponent bits, but less number of fraction bits. To do it, I can just write this expression in my query. So for each array element, I'm using the array map function. I will do this transformation. I will do bitwise AND with this bit mask, and I will keep only first 16 bits. Actually, it still will be floating 32 because there is no bfloat16 data type in ClickHouse, but the rest of the bits will be 0. And the point is that if you compress this data, like here, it will be compressed 2 times. Let's take a look. Okay, so we have the system columns table, and here is our column, and uncompressed bytes is 44 gigabytes, compressed is 19 gigabytes. And for another table, it was not compressed. So this is like the simplest way to compress vector representations. And it still works. The search gives the same results. With this truncated data type, we truncated it and saved twice the space, but the quality is not affected at all. So it suggests maybe we can truncate it even more to 8 bits. ClickHouse hugely outperforms on query patterns that would devolve into table scans in a raw store. Okay, I trust it. What other optimizations can we make? First of all, we can do pre-filtering. For example, we don't have to order everything by distance. We can cut off the distance by a certain constant first, and then order by. We can also lower the index granularity for our table even more. Maybe it will be faster. But actually, many of you are already asking, what about vector indexes? Do we have to scan these 30 million records? It is fast, it is less than a second. But what if we have billions of records? And there are many interesting types of indexes, like HNSW, NNOI, PQ, IVF, and there are many libraries implementing these indexes, such as Phase, NMSlib, NNOI again, DiskNN, Scan, Falcon. Why don't just plug in these libraries into ClickHouse and benefit from indexing? Maybe our queries will return just in a single millisecond. But actually, I did not want it. I wanted to experiment and build our own index directly in ClickHouse just for fun, using existing tools. And I use a method named random projections. So if you have a high-dimensional vector space, and you want to represent this vector space in a lower number of dimensions, but you still want the distance in the projected vector space to correspond to the distance in the original vector space up to a certain threshold, up to a certain error. And there is actually a mathematical proof that it is possible, but you have to, and the way to do it is to take a large number of splits of the space by hyperplanes. And for every split, calculate just a single bit of information. If the point on the one side of this plane or on the other side of the plane. And as a result, we will get a bit vector. If we take the same amount of bits, probably we will not lose precision too much. If we take a low number of bits, we will lose the precision definitely. And the question how to choose these hyperplanes. The answer is, let's choose them randomly. Take take 2 points from the data set, like this point and this point. Take the middle point and make a plane that is orthogonal to this vector between these points. So this plane will perfectly split these points to each other. And what I will get as a result, I got this. Look how beautiful it is. This is so beautiful. I want to put this picture into a frame. I want to pin this frame somewhere on the wall because it is just amazing. What is on the picture? I have taken a data set. I split it by random hyperplanes and then projected to just two-dimensional space. And here it is. All our data. Okay, how to do it in ClickHouse? We can use a simple insert select statement. So we will create a table with random hyperplanes, and to calculate that the point is on one or another side of this hyperplane, we do a scalar product to the normal to the hyperplane and compare it with 0. So in this case, we have normals, offsets, and we select from a table and calculate this. First of all, we have to calculate random normals from our data, and we do this, and we use 256 data points and insert 128 hyperplanes. Okay, and now we calculate this bit mask representation of our vector space. We will use just 128 bits, and it will be our vector index. And here we calculate this scalar product. This is the scalar product, and it is calculated. And we pack it into the bits. Let's see how it will work. The hypothesis is that if we take bit masks and calculate the number of distinct bits, which is named Hamming distance, it will correlate somehow with the original distance. But as we have only 128 bits, instead of this huge vector, it will be much faster. And as a distance, Hamming distance is represented in this way. We XOR these bit masks together. It will give bits where it is different, and we count these bits. Okay, and my experiment shown that it does not work. It does not work well. So what did I do? The second solution was to use this index only for pre-filtering, but order by the original distance. In this case, here is the approximate distance, and here is the original distance. And I filter by approximate distance with some high threshold, then order by the original distance. Let's take a look. Okay, here is my table. The vector is 28 gigabytes, but this bit mask is only 450 megabytes. So it is almost 50 times less. Let me do this query using this index. Okay, the results look relevant. Did you evaluate ClickHouse? How does this compare to ClickHouse? ClickHouse is another favorite. Okay, here are our distances. So looks like it works. Now let's add the preware, and it works, but it is not as fast. But results are about the same. Now, if we lower the threshold by approximate distance, it becomes faster, and results are the same. Can we lower this threshold even more? Let's try this. Oh, it starts to be 2 times faster, 0.4 seconds. And the results are the same. And if we filter even more, 25, oops, now the results are not totally, but they changed. Okay, and even more. Now it is fast, but it does not return much. That was a nice experiment. It gives like 2 times improvement, but I'm not sure if it's worth it. Sometimes full scan is just simple and powerful, and you don't have to worry about the precision. We can apply more tricks, like order the table by bit mask, and it will get a sort of implicit indexing. We can lower max block size. We can also change some settings. And we have built a prototype on this for searching the dogs, and apparently it also works. At least all the returned results are dogs, not cats. So I'm still satisfied, but frankly speaking, I like cats more than dogs. Okay, so the takeaways. There are specialized vector databases. There are a lot of specialized vector databases. But who cares? These databases can only do vector search. Maybe they do it quite well. But in ClickHouse, you can do not only search, you can do analytics, you can run your models, you can use pre-filtering, post-filtering. You can store multiple embeddings, multiple vectors. It works for any data size, not only for just millions of records, but billions of records. It is not limited by memory. It can scale out. It supports object storage. So you can do everything in ClickHouse. You don't even need specialized databases. Thank you.